We will discuss now nuclear spin statistics. We have already discussed that quantum mechanics requires that the total wave function be either symmetric or antisymmetric So, symmetric for bosons that we discussed and antisymmetric for fermions. With respect to exchange of any two identical nuclei. So, if we say the total wave function is psi total, so psi total must be symmetric if nuclei have integer spins or for bosons or antisymmetric if nuclei have half integer spins and for fermion. So, psi total, which is function of coordinate, suppose x we are saying here, and if we exchange the nuclei, we get psi total minus of x, okay. And this is suppose is for we consider here it goes to psi total, and this is for your for bosons, and psi total, if we exchange the nuclei, if we get minus psi total is for fermions. Okay, so we consider one homonuclear diatomic molecule like oxygen. So, for homonuclear diatomic oxygen molecule, so we consider homonuclear diatomic molecule O2 here, and we will discuss elaborately about nuclear spin statistics. So, for O2 molecule, the O16 nuclei have spin I equals to 0. So, these are bosons. Therefore, psi total for O2 molecule is symmetric, and this is an even function. Now, we know what is psi total, we discussed. Okay, psi total is nothing but psi transitional times psi rotational times psi vibrational times psi electronic times psi nuclear. So, psi total consists of 5 different degrees of freedoms: transitional, rotational, vibrational, electronic and nuclear motions. So, we need to investigate or we need to examine symmetry of each one of these wave functions of oxygen molecule for oxygen molecule upon exchange of two O16 nuclei. Note that we are permuting nuclei, not atoms. So, we need to examine the symmetry of each one of these wave functions for O2 molecule upon exchange of O16 nuclei. Okay. So, first we consider a transitional wave function. So, psi trans, it depends. So, psi trans depends only on the center of mass coordinate of the molecule So, this function is not affected by exchange of two O16 nuclei. So, we will not consider this, or it will not affect psi total. Okay. So, we will not consider this. Next is we consider psi vibrational. It depends only on distance between two O16 nuclei So, this coordinate is not affected by exchange of two O16 nuclei. So, this one also we will not consider. So, we will not consider this. Next, we discuss psi electronic. The ground state the ground electronic state rather the ground electronic state of O2 is sigma 3 G minus. So, this term symbol indicates or suggests that the electronic wave function is antisymmetric. So, this is odd function with respect to exchange of two O16 nuclei. So far we discussed about psi trans. Psi trans depends on the center of mass coordinate of the molecule. So, this function is not affected by the exchange of two O16 nuclei. Then psi vibrational, it depends only on distance between two O16 nuclei. So, this coordinate again is not affected by exchange of two oxygen nuclei. And then we considered psi electronic. So, the ground electronic state of oxygen molecule is 3 G minus 3 sigma G minus. So, this term symbol suggests that the electronic wave function is antisymmetric. So, this is an odd function with respect to exchange of two O16 nuclei. So, next we consider psi rotational. So, we consider rigid rotor model here. So, rigid rotor rotational wave functions are spherical harmonics, right. And psi rotational when j is 0, 2, 4, 6, when j rotational quantum number j is even, this is symmetric with respect to exchange of two O16 nuclei. So, this is even function. And psi rotational when j values are odd like 1, 3, 5 etc., the psi rotational is antisymmetric with respect to exchange of two O16 nuclei. Okay. Now, we said that psi nuclear, since O16 nucleus has nuclear spin I equals to 0. So, O16 nuclei are bosons. Okay, so this is even function. Okay, so we'll these are first these are bosons, and then we have 2i plus 1 times I plus 1 symmetric or even nuclear spin states, and they are termed as ortho hydrogen rather, and 2i plus 1 times 2i plus 1 times I antisymmetric or odd nuclear spin states, and we call them para. Okay, so for I equals to 0, we get 1 symmetric nuclear spin state or ortho, and if we substitute I in 2i plus 1 times I, we get 0 antisymmetric nuclear spin state or para. So, in general we will have 2i plus 1 times I plus 1, where I is the nuclear spin, number of symmetric nuclear spin state, and 2i plus 1 times I, number of antisymmetric nuclear spin state. And for symmetric spins we call ortho, and for antisymmetric we call para. Why they are termed as ortho and para, we will discuss. So, if we substitute a value of I in 2i plus 1 times I plus 1, we get 1 symmetric nuclear spin state or ortho, and 0 antisymmetric nuclear spin state or para. So, only ortho oxygen is possible. Okay. So this is even. So, only psi nuclear for oxygen is even. Okay, so because there is no antisymmetric nuclear spin state for O2 molecule. Okay, so psi nuclear we get only even. Now we consider psi total. So psi total, we discuss psi total is psi electronic times psi rotational times psi nuclear spin state times psi transitional and times psi vibrational. They are also there, but we will no longer consider this. Why? That we discussed above. So psi total is, as we know, psi total is even. So psi electronic we got odd, because the ground electronic state of oxygen molecule is 3 sigma g minus, which is an odd function. Now psi rotational, first we put psi nuclear is here even. So in order to make psi total even, psi rotational has to be odd. Okay. So, it says, so J equals to 1, 3, 5, these are possible. But if we consider psi total as even, then if we consider psi rotational as even, then psi total is even equals to odd times even times even. So, this is not possible, because we get, if we multiply odd times even function, we get odd function. So, only in ground state of oxygen molecule, only odd rotational levels are possible. Okay. So, what I said here is, so we can say that, okay, for O2 molecule, therefore, for oxygen molecule in the ground state, or in the ground electronic state, cannot exist in even rotational states, because odd times even does not match, or does not result, or does not produce an even function as required by quantum mechanics. Okay. So, for O2 molecule, therefore, for O2 molecule in ground electronic state, Q rotational we can write J 1, 3, 5 etc. times 2J plus 1, this is the degeneracy factor that we discussed already, minus times J plus 1 times theta rotational by T, or we can write up minus J times J plus 1 times theta rotational by T dA, and this half term we already discussed. This is nothing but symmetry, appears due to symmetry number. Okay. So, appears due to symmetry number. We consider one more example here, and for that we consider ortho and para hydrogen. So, next we consider ortho and para hydrogen. The molecules of hydrogen can exist in two forms depending on the spins on the two hydrogen nuclei. The molecules of hydrogen can exist in two forms depending on the spins on the two hydrogen nuclei if both the nuclear spins are parallel, the molecule is called ortho hydrogen, and if the spins are antiparallel, it is referred to as para-hydrogen. So, this nomenclature comes from, if we consider the disubstituted benzene. So, this nomenclature means ortho and para comes if we consider disubstituted benzene here. So, this is one and this is one. Okay. So, this is like your both are parallel. Okay. And para means they, it is like again we consider disubstituted benzene here. Okay. So, if we consider disubstituted benzene and the second substitution is in para position, we get like this. So, this is like the spins are antiparallel. So, this is spin of one hydrogen nucleus and this is the spin of another hydrogen nucleus, and they are, when they are parallel we call them ortho, and when they are antiparallel we call them para, okay, para hydrogen. So, now it is clear that okay, why this ortho and para hydrogen, why these nomenclatures come. The spin on a hydrogen nucleus on hydrogen nucleus, so I is half, right. The presence of nuclear spins leads to very interesting consequences for the populations of the rotational states. And on a macroscopic scale, has consequences on measured entropies and heat capacities. as well. So, the presence of nuclear spins leads to very interesting consequences for the populations of the rotational states, and on a macroscopic level or scale has consequences on measured entropies and heat capacities as well. The total, like before, we can consider the total partition function for H2 can be written as Q rotational is Q electronic times Q vibrational times Q rotational times Q transitional times Q nuclear. Okay, and from here we get psi total is psi electronic times psi rotational times psi nuclear times psi transitional and psi vibrational. And we just discussed that we can safely neglect, we do not consider psi transitional and psi vibrational. So, psi total depends on psi electronic, psi rotational and psi nuclear. In the ground state, or in the electronic or the terms or the ground sets, the ground electronic state for H2 is 1 G sigma. So, this is an even function. And since each nuclei has a half integral spin, so psi total is an odd function. Okay. So, psi total is odd, and we get psi electronic is even. Now, we consider psi rotational. Okay, so psi rotational can be even or can be odd. Okay, so total is odd, psi total is psi electronic times psi rotational and psi nuclear. This is odd, psi total is odd, this is even. So, if psi rotational is even, then psi nuclear has to be odd, right. Then only we get odd equals to even times odd, or if psi total is odd, psi electronic is even. If psi rotational is odd, then psi nuclear has to be even, right. So, combining the nuclear spin and the rotational parts, we see that the product psi rotational times psi nuclear must be antisymmetric. antisymmetric means antisymmetric with respect to exchange of two H1 nuclei. Okay. To accomplish this, the singlet nuclear states called para must be combined with the even rotational functions, right? Because the singlet nuclear spin state or para state means antisymmetric, means odd, so must be combined with the even rotational functions. And the triplet nuclear states must be combined with, so triplet nuclear states means ortho, must be combined with the odd rotational states. So, the rotational partition functions for ortho and para hydrogens are Q rotational is 3 times and this is nothing but Q ortho. And Q para is 1 times j goes from 0 to 4 etc. to infinity 2j plus 1 e to the minus j times j plus 1 theta rotational by t. Okay. So, in this expression we know the theta rotational, where theta rotational as usual is the rotational temperature, right. The total partition function consisting of ortho and para hydrogens you can write Q rotational as well as nuclear is 1 times j goes from 0 to 4 etc. when all j values are even, plus 3 times when all odd j values, sum over all odd j values times 2j plus 1 e to the minus j times j plus 1 times theta rotational by t, where 2j plus 1 in this expression is nothing but degeneracy of jth level. Thus, the ratio of ortho to para hydrogens are at thermal equilibrium you can write in ortho the ratio in ortho by in para So, we have got the expression for number of ortho and para hydrogens at thermal equilibrium. Okay. So, at high temperature the two summations in the above expression are equal. Okay, so, we get n ortho by n para is 3. Okay, so, at high temperature we have 3 times more number of ortho hydrogen than para hydrogen. At low temperature we get n ortho by n para goes to 0 as t goes to 0. Now, a good experimental verification of the above analysis is a comparison between the calculated rotational heat capacities at constant volume this CV can be calculated from the partition function expression. From the partition function expression we get we can calculate average energy, and if we differentiate the average energy with respect to temperature at constant volume we get CV. Okay. So, we verify this. Okay. So, we plot next, we plot the heat capacity at function of temperature, the plot of heat capacities as a function of temperature. So, if we plot heat capacity as a function of temperature, the plot looks like we are plotting Cv by N kV versus temperature in Kelvin. So, in the above plot, in this plot, in the above plot, the curve marked exp gives experimental, gives the variation of Cv the variation of Cv as temperature changes. The curve EQ represents the data for an equilibrated mixture of ortho and para hydrogen. The curves ortho and para refer to the heat capacities of pure ortho and pure para hydrogens respectively. Initially, it was a puzzle as to why the experimental heat capacity values of hydrogen hydrogen molecule differ from the calculated value. In fact, the experimental data agree very well with the below equation. So, CV rotational nucleus is 3/4 times CV plus 1 for ortho plus 1/4 times CV for para. The reason for this is that when H2 molecule is cooled down from a higher temperature, the ortho-para ratio continues to remain 0.75 by 0.25, the high temperature value. Because the ortho-para interconversion rate is very, very small. And we do not reach equilibrium composition unless a catalyst such as activated charcoal is added to the mixture. The above expression of CV corresponds to a frozen high temperature mixture. Mixture of ortho and para hydrogen. In the presence of the catalyst, the experiments also give the curve labeled as equilibrium in the above plot. This is indeed a nice case where the experiments support not only the methods of statistical thermodynamics, but also the antisymmetry principle of bosons and fermions. So, this is indeed a nice case. The above examples we have considered, where the experiments support not only the methods of statistical thermodynamics, but also the antisymmetry principle of bosons and fermions. Thank you.